Hello everyone, welcome back to MindMatrix YouTube channel. So in this video, we will be talking about Bayes theorem. So I hope if you are following the sessions, if you haven't seen, just go and check out because we have started from scratch. We have started from exactly permutation combination to learn the basics of counting, which will be useful for probability concepts. And then further we discussed about probability, their interpretation, which becomes an important part in understanding machine learning as well. Okay, then we discussed about the axioms, the laws, and further if I talk about, we discussed about conditional probability, and there were some very fine important concepts as well, okay, which is generally being missed out when we discuss this probability chapter and some other gate exams, okay. But because it's DA exam, it is very important to understand all these intricacies. So I hope you have followed that. So now we'll be talking about Bayes theorem, okay. So here is a quick intro about myself. I'm upcoming data scientist at Lowe's India, and I'm pursuing M.Tech AI right now in IISc Bangalore. This is my last semester over here. And further, you can see about my teaching experience and achievements. Okay, so let's move further. So today's agenda would be definition. We'll be talking about Bayes theorem and total probability. These two are the important concepts we'll be talking about, and then we'll have a look at the examples. Basically, with the help of example, we'll be learning why do we exactly need Bayes theorem and total probability. Okay, and then we'll discuss about some important terms which are very important for machine learning and machine learning point of view. Those are very important, and then further we will be solving questions in our next session. Okay, part 2 of this Bayes theorem and total probability. So let's move further. So here is the first definition of the day of the session, which is total probability. So I hope if you have been following me on this channel, so I have already discussed about this thing. I have already discussed about partitions earlier, and you have already seen this kind of expression as well. Let me just write two things. So first thing, you know about the partitions already, okay. And the second thing is you must be aware, if you have been following, if you are not following, please go and learn this concept, though I'll be giving a brief overview over here, but still, to be more comfortable, just you can see the previous lectures. And the other thing is, I can write any event, probability of any event, like this: a1b plus p of a2b plus up to p of a and b. And when I'm writing two events all together like a1b or a2b, it means simply, if I am writing aib something like this, it means ai intersection b I am talking about. AI intersection B I'm talking about. So I hope you remember this thing, partition. So basically what I'm referring to is A1, A2 up to AN are the partition of sample space. Okay. And any event B can be written something like this. Okay. This must be known to you. If you don't know, then even it's fine, because I'll be covering that over here as a proof, because that's important, because you have to do it a number of times when you won't be having a basic idea that okay, how I can approach this kind of problem and how I can break it up. So see, if I have this thing that okay, a1 up to a and are my disjoint sets. Disjoint sets means there is nothing in common between any pair of these sets. Okay, that means their intersection is empty set or phi. Okay, null set. And if I combine all of them, that creates my sample space. So what I can do is something like this. Then I'm just giving a proof over here, okay, which is important to understand how does this come. So P of B, which I can write it as P of B intersection sample space, because I know their intersection is going to be B itself. Now, because my sample space is nothing but union of A1, A2, union up to N, okay, union up to A of N. Now it can be further written as, if you know these basic law of set theory, basic laws from set theory, you can write it as P of P intersection P of A1 union B intersection A2 union B intersection AN. Now, if you remember this part, when we discussed it already, that okay, if we have A1 union A2 union up to AN, and all of these are disjoint sets, all of these are disjoint sets, that means this is something else. Okay, let me just write, okay, not P, let me just write it as P of Q, yeah, Q1 Q2 union up to Q1, union up to Q1. So if I want to calculate the probabilities of events Q1 union Q2 union Q1, and all of these are disjoint, that means there is no intersection. Right now I'm not saying that it's a partition or not, I'm just saying that there is nothing in common between them. They have intersection 5. There is nothing common in between any of them. Then I can reduce it to sum of individual probabilities. That means P of Q1 event plus P of Q2 event plus P of Q3 event, and something like this. Okay, it goes up till P of Qn event. If there was nothing in common, remember when we started probability, this is the thing which is coming from there. Okay, if you haven't seen, please go and check. Please watch out the previous lectures. Okay, so what I can write it for this, what I can write over here for this, I can write it as probability of P B A intersection this one plus there is this thing very important. Why are these disjoint now? Why are these disjoint? See, because A1, A2, AN over here were disjoint, and if I take the intersection with B, so whatever I'm getting over here, let's say this is B1 dash, let's suppose this is B2 dash, let's suppose this is BN dash, then B1 dash, then this B1 dash, B2 dash, up till Bn dash. These forms partition of B event. These form partition for B event. Okay, because that means if I combine all of them, it will create B, which I already know, because ultimately I must, because I have started from over here, so I must be getting B, and there is nothing in common between these B1, B2 dash, Bn dash, because you already know, because A1, A2 were disjoint, hence their intersection with any of the set will also be what? A kind of disjoint. That means nothing would be common in between them. So hence these are also disjoint, hence I can break it up or decompose it into sum of individual probabilities and so on. That means I can write it as P of BA1. This is the usual notation I use, which is P of AB is equal to P of A intersection B. This is what I'm talking about. Okay, AB means A intersection B I'm talking about. So this will be P of A or P of B A2, P of B up to P of B AN. Okay, I hope this thing is clear. Now you have already seen conditional probability in the last video. Okay, you have already learned that. If you have learned that, you already remember this thing, that P of B given A is nothing but P of AB divided by P of A. So if I want to find out P of AB, I can do that by multiplying these two, this value and this value. So what I can write over here, it would be P of B given A1 into probability of A1 plus probability of B given A2 into probability of A2 and so on. So if it is repeating till n, then I can write it as probability, basically probability of B given AI into probability of AI. And because I'm talking about their addition, so I can use the summation from I equals 1 to n. And that's what we have over here, law of total probability. Now, what does this mean? This basically means I can decompose probability of event into summation of conditional probabilities over here. Sum of conditional probabilities over here, okay, which is multiplied by probability of individual events. I hope this idea is clear. Now, how is this being used? We'll have a look at that in our next slide with the help of an example. So the point is, I can decompose an event and write it in terms of conditional probabilities. This was the holistic, like this was completely different event B, and then somehow I have written it in form of, conditional probabilities that given some other event, I can calculate this thing. And there is a procedure for it, which is like summation of each of these. Now, how do we do this? Let me just give you a short example over here, and then we'll solve a numerical as well on the basis of it. So let's suppose you want to find out that, okay, what is the probability of marking a question correctly? Okay, suppose there are MCQ questions in a test. There are MCQ questions in a test, and either you know the answer, or you guess the answer for the MCQ. Either you know the answer or you guess the answer for an MCQ. Now, if you want to find out what is the probability of making a correct option, or basically getting a correct, getting your question correct, basically what I'm saying is correct answer, probability of giving a correct answer. If you want to find it out, now it depends upon a number of things. Over here you can see that, okay, simply I need to find probability of giving a correct answer. But if you see it from another, different perspective, you'll get to know that correct answer will depend upon two things. Either I was knowing the answer or I was guessing it. So it is decomposing it into like this correct answer stuff. This concept is decomposing into two parts, whether I have whether I have guessed the answer or I was knowing the answer. Okay, so in that case, how can I write this? Let me just write it as C only. Correct answer means C. So probability of getting a correct answer given I know the answer into probability of knowing plus probability of getting a correct answer given I have guessed the answer, and then probability of guessing an answer. Now you already know that for any question, either you will be knowing or you won't, or you will be guessing. So there is like this creates a partition, yes or no. There are only two things: either you guess an answer or you give the correct answer. Okay, if you don't know the answer, then you will be guessing. So it's a partition. So over here, K and G, which I'm talking about, K and G. K means you know the answer, G means you're guessing. This creates a partition, and on the basis of that, if you know the answer, the probability would be something. If you are guessing, then probability of getting an answer correctly would be something like that, would be some value would be there associated with it. And that's how you calculate the probability of getting a correct answer. Overall, we'll have a example for this thing as well of correct answer later on, okay, which we will be looking at later on. So I hope you have got this basic idea that my law of total probability helps me in decomposing probability of event into multiple parts, and those multiple parts are nothing but conditional probabilities multiplied by probabilities of individual events. Conditional probability multiplied by probability of individual events. That is how you get your probability of an event. Okay, so I hope this idea is clear. Whenever you have an abstract idea, you don't know the exact way of calculating the probability, you basically decompose it into multiple parts in a form of disjoint events. Okay, like the example is over here already clear of attempting a question within an exam, which is an MCQ question. Okay, so let's move further and have a look at a proper example where we will be solving the problem. So this is an example which was being asked in your sample paper of IISc, which is already given on the website for the DA. Okay, so this question is from your IISc sample paper of DA exam. So let's see this, and this is based on total probability law only, and we'll solve this question in two ways. Okay, one is the basic idea, basic intuition, how you can solve that, and the another being that okay, using the exact concept which is being used over here. So this has been told that class contains 60% of the students who are incapable of changing their opinions. Okay, and 40% are there who change their mind at random. Okay, so it's like if any student is being asked about something, okay, to present an opinion, so 60% students are like they will stick to their opinion only. Okay, they won't be changing. If you know just force them, if you just tell them any information, they would be like, no, I would like to stick to my opinion, that's it. But 40% students are a bit random. They can change their opinion anytime if they feel like my opinion is may or may not be correct. Okay, now they change their mind with the probability of 3.3. That means if they feel that okay, my opinion is not correct, then the probability with which they can change their opinion is zero point 0.3. Okay, now between so this is between subsequent votes on the same issue. So it's like something like there is some kind of issue which is being discussed, and some votes are being asked, okay, how many are in the favor of this thing or that thing. Then some students are there who are like, okay, they stick to their opinions. Okay, but some students are like, after some time they are like, no, I would like to go with the other side of the story. For an example, let's just take a simple example of reservation. So some students would be like, okay, reservation must be there. Some students would be reservation must not be there, and they are sticking to the point. Okay, like once we have delivered the lecture, they are like, fine, okay, they have made a concrete choice that okay, I'll stick to reservation must be there or not there. So those are like 60% of the students. But then there are some students who initially said reservation must not be there, but when somebody told some presented some fact, some information, then they were like, oh, I have made a wrong choice, so they change their mind. But then there is a probability for that if they are changing their mind, it is with a probability of zero point 0.3 on the same issue, the reservation. So like on the both the sides, if somebody was saying reservation must not be there, then he's saying reservation must be there. And if there was some student who was saying reservation must be there, he's changing it to reservation not be there with a probability of 0.3. I hope the idea is clear. Okay, then what do we need to calculate? We need to calculate probability. We need to calculate the probability of a student randomly voted twice in the same way. Basically, when two times, okay, voted twice, two times or twice, basically one and the same thing. Two times a student is giving same answer, same opinion. So when a student is being asked, let's say any random student we are talking about, and we ask him two times, then in between that he presents the same opinion. What is the probability that he presents the same opinion? Okay, now here is the thing. Now if that student is giving same opinion, there are two things. Either that student was one of these students who stick to their opinion, or there was this student as well who changed their opinion, but there was some probability associated that zero point 0.3 only, 0.3 times, 30% of the times only they change. So 70% times they do not change. So maybe that student who was picked up was someone who may change, but he did not change his opinion. Okay, so both the things can happen. So how do we solve this problem? It is very simple. Let me just write a proper expression to find it out. So probability of of voting twice in same way. Let me write it in a proper, comprehensive way. Voting twice in same way. Okay. And let's suppose This I am denoting by B. This event I am denoting by B. That is, I would like to calculate P of P. So I can break it into two parts. What? Probability of B given A1 into probability of A1. I'll tell you what exactly is A1 and A2, and probability of B given A2 into probability of A2. Now A1 is event when I'm talking about the student is incapable of changing mind. Student is incapable of changing mind. Is incapable of changing mind. Okay. And A2 is he changes it randomly. Student changes opinion randomly. Student who changes opinion randomly. I hope all the events are clear. Now, if I would like to find out that student will vote same twice, what is the probability if he was this kind of student? If he was this kind of student, the probability is 1. Because if he is the student who does not change his opinion, then whatever he voted first time, he would be voting same thing. So there is 1 probability for that because he won't be changing. What is probability of such kind of students? What is the probability of such kind of students? There are 60% of the students. That means 0.6 is the probability of such students. Now, what is about this thing? That okay, if given that the student is someone who can change their opinion randomly, then what is the chance that okay, he will be voting same way twice? He will be voting same way twice. So over here the value was 0.3, which means the probability with which he can change. But over here I'm talking about he does not change the opinion. So that is going to be 1 minus 0.3. That is 0.7 would be the probability that given a student who changes his mind will vote same way twice. It is 0.7. It is 0.7 over here. Okay. Now, what is the probability of this kind of student? What is the probability of getting such kind of student? They are 40% of total. That means 0.4. So what do I get? 0.6 plus 0.28, that is 0.88. I hope the idea is clear. Okay. So 0.7, what is this? Probability that student will vote twice in same way given that student could change the opinion. If he could change the opinion, then the probability would have been 0.3. But because he has voted twice same way, so that means it is the other side. That means the probability which has been used over here is 0.7, because with 0.7 probability they answer same way. Okay. And how many, or what is the probability of such kind of students? 0.4, because those were 40% of the students. So the answer is 0.88. I hope the idea is again clear over here. Now there is another thing which is important to understand, how we could have solved it, in a simple fashion. This is the proper way of solving it. Okay, this is the exact detailed and conceptual way of solving it. Now if I say, could we solve it in a better or a shorter way? Yes. What could have been that way? Let's see that. So it is like, okay, all the students we are having, then I know 60% don't change opinion. 40% may change opinion. Okay, it's not like that 40% of will change. It is like 40% may change. Now within those, 30% change the opinion. Change the opinion, because 30% is the chance. Okay, change opinion. And 70%, because the other part, if 30% change, then 70% do not change. And what exactly you were looking for? That if a student randomly chosen has voted twice in the same way, that means the student didn't change his opinion. Student didn't change his opinion. What you are looking for? You are looking for this and this. You are looking for this and this. So what is this? This is 0.6 over here. Now what is this? 0.4 into 0.7. 0.28 plus 0.6, which is 0.88 again. Or what you could do was subtract this from the overall probability, which is 1. Subtract this thing from 1. You will get the probability such that student does not change his opinion. So 1 minus, what is this? What is this? 0.4 into 0.3. Which is again 1 minus 0.12, which is 0.88. I hope the idea is clear. Okay, this way also we could have solved it. Total minus this thing, which also represent do not change opinion. And if I like to calculate directly don't change opinion students, then I can go by individual counting them. And the one way we have already seen was using our law of total probability. I hope the idea is clear. Okay, and we have got to know exactly why do we need law of total probability, why do we need to decompose it further. Okay, because there may be some smaller events with the help of which we can find out the probability of particular event. Okay,